Welcome to the class of Advanced Stats and Econometrics. In today's lecture, we are going to discuss the remaining part of the cluster analysis, the objectives of the cluster analysis. So basically, cluster analysis is used for taxonomy description, identifying natural groups within the data simplification, the ability to analyze groups of similar observation instead of all individual observation, the relationship identification, the simplified structure from cluster analysis portrays relationship not revealed otherwise. Theoretical, conceptual, and practical consideration must be observed when selecting clustering variable for cluster analysis. Only variables that relate specifically to objectives of the cluster analysis are included. Since irrelevant variables cannot be excluded from the analysis once it begins. Variables are selected which characterize the individual objects being clustered. Stage 2 Research design in cluster analysis. 4 questions. Is the sample size adequate? Can outlier be detected? And if so, should they be deleted? How should object similarity be measured? Should the data be standardized? Measuring similarity. Inter-object similarity is an empirical measure of correspondence or resemblance between objects to be clustered. It can be measured in a variety of ways, but three methods dominate the application of cluster analysis: correlational measures, distance measures, association. Type of distance measures. First is Euclidean distance measure, which is most widely used. Second is squared or absolute Euclidean distance. City block or Manhattan distance, Chebyshev's distance, Mahalanobis distance, d square. Research design in cluster analysis. The sample size required is not based on statistical consideration for inference testing, but rather sufficient size is needed to ensure representation of the population and its underlying structure, particularly small groups within the population. Minimum group size are based on the relevance of each group to the research question and the confidence needed in characterizing that group. Research design in cluster analysis. Similarity measures calculated across the entire set of clustering variables allows for grouping of observation and their comparison to each other. Distance measures are most often used as a measure of similarity, with higher values representing greater dissimilarity. Distance between cases, not similarity. There are many different distance measures, including Euclidean straight line distance is the most common measure of distance. Squared Euclidean distance is the sum of square distance and is the recommended measure for the centroid and Watt's method of clustering. Mahalanobis distance account for variable intercorrelation and weights each variable equally. When variables are highly intercorrelated, Mahalanobis distance is most appropriate. Less frequently used are correlational measures where large values do indicate similarity. Research design in cluster analysis. So we are going to discuss given the sensitivity of some procedure to the similarity measures used, the researcher should employ several distance measures and compare the result from each with other results or theoretical known pattern. Outlier can severely distort the representativeness of the data if they appear as structure clusters that are inconsistent with the research objective. They should be removed if the outlier represents aberrant observation not representative of the population, observation of small or insignificant segment within the population which are of no interest to the research objective. They should be retained if representing an undersampling poor representation of relevant group in the population. In this case, the sample should be augmented to ensure representation of these groups. Research design in cluster analysis. Outlier can be identified based on similarity measures by finding observation with large distance from all other observation. Graphic profile diagrams highlighting outlying cases. Their appearance in cluster solution as single member or very small cluster. Clustering variables should be standardized whenever possible to avoid problems resulting from the use of different scale values among clustering variables. The most common standardization conversion is 0 G score. If groups are to be identified according to the individual's response style, then within case or row centering standardization is appropriate. Stage 3 assumptions of cluster analysis. So representativeness of the sample, impact of multicollinearity. Assumptions in cluster analysis: input variables should be examined for substantial multicollinearity, and if present, reduce the variable to equal number in each set of correlated measures. Use a distance measure that compensate for the correlation like lowest distance. Take a proactive approach and include only cluster variables that are not highly correlated. Stage 4: deriving clusters and assessing overall fit. The researcher must select the partitioning procedure used for forming cluster: hierarchical, non-hierarchical. Decide on the number of clusters to be formed. Two type of hierarchical clustering procedure: agglomerative method, built up; divisive method, breakdown. So in agglomerative, we begin with all the cluster, each observation is a cluster. So if there are 100 observations, we have 100 cluster, and we keep adding two clusters which are closest to each other, and one by one we will reach to one cluster ultimately. So this is, we begin with large number of cluster, each observation is a cluster itself, and in the divisive we begin the process otherwise. We begin all observation in one cluster, then divide it into two, then three, then four. So dendrogram illustrating hierarchical clustering. So in first stage, say cluster 1 and 2 got merged, then 5 and 6 got merged, and so on. This merging of clusters stops when ultimately we have one cluster. So that is agglomerative. Divisive is other way around. How agglomerative hierarchical approach works: start with all observation as their own cluster. Using the selected similarity measures, combine the two most similar observation into a new cluster now containing two observations. Repeat the clustering procedure using the similarity measure to combine the two most similar observation or combination of observation into another new cluster. Continue the process until all observations are in a single cluster. Agglomerative algorithm: single linkage, nearest neighborhood. So you are looking at cluster, and the distance between cluster is through single linkage. That means the shortest distance between any two members of these two clusters. Complete linkage is other way around. It is the farthest neighbor. So maximum distance between the members of two clusters. Average linkage is just average of this, and centroid method and ward method we'll discuss, because in the centroid method and average linkage is average of all the distance, and centroid method we are looking at the distance between centroid. So here we have example of single linkage joining dissimilar A cluster A and B. So we have shown A and B and C, and these are the examples through which we can say that there are many observations. If you look at the minimum distance between any two, or the maximum or the average. So shortest is shown as single linkage, longest as complete linkage. How non-hierarchical approach works: specify cluster seeds. So assign each observation to one of the seeds based on similarity. Selecting seed points: researcher specified, sample generated. Non-hierarchical cluster software. So SAS has fast close. So that is the fast cluster. First cluster seed is the first observation in the data set with no missing value. SPS has quick cluster. So seed points are user supplied or selected randomly from all the observations. Non-hierarchical clustering procedure: sequential threshold: select one seed point, develop cluster, then select next seed point and develop cluster, and so on. Parallel threshold: select several seed points simultaneously, then develop cluster. Optimization is permitting a reassignment of the object. Deriving hierarchical cluster. Hierarchical clustering method differs in the method of representing similarity between clusters, each with advantages and disadvantages. Single linkage is probably the most versatile algorithm, but poorly delineated cluster structure within the data produce unacceptable snake-like chains of cluster. Complete linkage eliminates the chaining problem, but also considers the outermost observation in the cluster, thus impacted by outlier. Average linkage is based on the average similarity of all individual in a cluster and tend to generate cluster with small within cluster variation and is less affected by outliers. Centroid linkage measures distance between cluster centroid and link and like average linkage is less affected by outliers. What's it based on the total sum of square within cluster and is the most appropriate when the researcher expects somewhat equally sized cluster, but it is easily distorted by outliers. Deriving cluster. Selection of hierarchical or non-hierarchical method is based on hierarchical clustering solutions are preferred when a wide range even all alternative clustering solution is to be examined. The sample size is moderate under 300 to 400, not exceeding 1000 or a sample of the larger data set is acceptable. Non-hierarchical clustering methods are preferred when the number of clusters is known and initial seed points can be specified according to some practical, objective, or theoretical basis. There is concern about outliers since non-hierarchical methods generally are less susceptible to outliers. Deriving cluster combination approach using hierarchical approach followed by non-hierarchical approach is often advisable. A non-hierarchical approach is used to select the number of cluster and profile cluster centers that serve as initial cluster seeds in the non-hierarchical process. A non-hierarchical method then clusters all observation using seed point to provide more accurate cluster membership. Interpretation of the cluster. This stage involves examining each cluster in terms of the cluster variate to name or assign a label accurately describing the nature of the clusters. Validation and profiling of the cluster. Validation, cross-validation and criteria validity. So profiling, describing the characteristic of each cluster to explain how they may differ on relevant dimensions. This typically involves the use of discriminant analysis or ANOVA. Deriving the final cluster solution, there is no single objective procedure to determine the correct number of clusters. Rather than researcher must evaluate alternative cluster solution on the following consideration and select the best solution. Single member or extremely small clusters are generally not acceptable and should generally be eliminated. For hierarchical method, ad hoc stopping rules based on the rate of change in the total similarity measure as the number of cluster increases or decreases are an indication of number of cluster. For all clusters should be significantly different across the set of clustering variables. Cluster solution ultimately must be theoretical. Validity assesses through external validation. Interpreting, profiling, and validating cluster. The cluster centroid, a mean profile of the cluster on each clustering variable, is particularly useful in the interpretation stage. Interpretation involves examining the distinguishing characteristic of each cluster's profile and identifying substantial difference between cluster. Cluster solution failing to show substantial variation indicate other cluster solutions should be examined. The cluster centroid should also be assessed for correspondence with the researcher's prior expectation based on theory or practical experience. Interpreting, profiling, and validating clusters. Validation is essential in cluster analysis since the clusters are descriptive of structure and require additional support for their relevance. Cross validation empirically validates a cluster solution by creating two subsamples, randomly splitting the sample and then comparing the two cluster solutions for consistency with respect to number of clusters and cluster profile. Validation is also achieved by examining difference on variables not included in the cluster analysis but for which there is a theoretical and relevant reason to expect variation across the clusters. Steps in cluster analysis. So we need to select the variable, determine if the cluster exists. To do so, verify the clusters are statistically different and theoretically meaningful. A logical name can be assigned. Decide how many clusters to use. Describe the characteristic of derived cluster using demographic and psychographic, etc. Variable selection. Variables are typically measured metrically, but techniques can be applied to non-metric variables. Variables must be logically related to a single underlying concept or construct. So here is the example in which we are going to see that the clusters are combined at different stages, and then when it was after merging, when it will reappear in the next stage, and what was the last stage where it first appeared. This is just the agglomeration schedule. It is showing the result of cluster combination, when at what stage which two clusters got merged, before that when it appears first appears last time, and next stage, what is the next stage where it is going to appear. Say for example, first stage is 1, cluster 3 and cluster 94 are merged, and the merged cluster will next appear in stage 9, 18, and so on. So these are the results of the cluster analysis. So here you can see that mean value, mean centered value cluster numbers are shown 1, 2, 3, 4, 1, 2, 3, 4, and F values are shown, and the variables are product quality, technical support, and sales force image, new product delivery speed. So cluster mean for actual data plotted, and cluster mean from mean centered data plotted, and reference for all this is a book titled Multivariate Data Analysis, 8th edition, Engage Learning. Authors are here, Babin, Anderson, and Black. That's it for today's class.